In this example, we're going to basically build an exponential model for some information given. So in this example, we know that a bacterial culture was 300 after 15 minutes and 1700 after 30 minutes. So I think there's some things to highlight in here. So the first thing is that we have an exponential function, right? So the function should look like um, a to the x equal to a e to the kx. Now, the second thing we want to make sure and notice that the time frame. So notice time is in minutes. So we just need to make sure that everything is in minutes. So if we have 15 minutes, 30 minutes, then everything in our problem should also be minutes. So this last part, when it says when, we're going to find the time in minutes. And the last thing I think we need to note here is that there are two pieces of information. They give us that when the time is 15 minutes, that the culture was 300, and when the time was 30 minutes, the culture was 1700. So we can see that we have two ordered pairs, and then that would tell us that X is going to be the time in minutes, and then the A would be the number of bacteria. I mean, you could see that it grows pretty fast. Okay, so let's go ahead and find the initial size of the culture. So that's probably going to take a little bit because if A of X, so find initial. So if we have A of X, that is equal to little a e to the kx, then really we're trying to find a, and all we really know are these two pieces of information, right? Those two ordered pairs. So let's go ahead and do that. The first thing we know is that the amount is 300 when a e to the k, and then our time would be 15 minutes. And then we do know when the culture is 1700, that this would be equivalent to a e to the k times 30. So what I like to do here is notice that if I make this look a little nicer, we get 300 equal to a e to the k 15k. And then here we get 1700 equal to a e to the 30k. So we don't know what k is, so notice that we have to solve for k. And so we have to solve for k in order to find little a, right, the initial. So we could go ahead and find the k easily because we do know that k is going to be, in this case, the growth rate. And the growth rate would be just solving these two for a. We could set these equal to each other and solve for k. So a could be equal to, here in this case, 300 over e to the 15k. And so here we would have A is equal to 1700 over e to the 30k if I divided each side by the base e to that power. So if I do that, then I could solve for k in this case, where if I put a equal to a, meaning 300 over e to the 15k is equal to 1700 over e to the 30k. And just doing some algebra in this case, we could easily see that it'll be 300 e to the 30k equal to 1700 e to the 15k. And then if I just keep going, I'll get 300 over 1700 equal to I'll get e to the 30k over e to the 15k, which is equal to 1700 over 300. And then this becomes, using some exponent rules, right? This becomes 15k, 30k minus 15k, and this is equal to 17/3. And then just finding the natural log of each side, and as we know what k equals, we know that the natural log of 17/3 divided by 15 is equal to k. And so at this point, we know that that would be, if we put it in the calculator, natural log of 17/3 divided by 15, we would get 0.1156. So that's just solving for k. So at this point, we can go ahead and go to the part where we can solve for a. So if a is equal to, let's just take this one. If a is equal to 300 over e to the 15k, then I know a can be 300 over e to the 15 times 0.1156. So if I put that in my calculator, I would go ahead and get 300 divided by E 1156 at 15 times 0.1156. So that'll be 52.97. Great, so this is the first part. So the first part is always going to be the longest, especially when you have to find a missing parameter of your exponential function. And so part B now would be find the doubling period. So the doubling period would be when the original culture doubles. So in this case, you would have two, you'd want to find X when you have 2 times A as your amount. So in this case, doubling the 52.97, so you would have 2 times 52.97, and that would just equal the exponential function 52.97 times e to the 0.1156 x. Now, this seems kind of redundant and silly because you're like, wait, those two just reduce out, and you're just really left with 2 is equal to the base of the k to the k x. And I would say, yeah, that's exactly it. So now we can go ahead and solve as we know. And the doubling time will always be the natural log of 2 divided by the k, which is 0.1156. And then we can go ahead and put that in the calculator to get the approximate doubling time. So if we do that, we have now going to functions and going to the natural log of 2 divided by the k 0.1156. And that would be 5.996, so about 6 minutes. So I would say about 6 minutes. Okay, so that is B. Okay, and then C would be find the population after 70 minutes. So if the population is after 70 minutes, so we need to find A when X is equal to 70. And that's an easy plug and chug. So we're just finding A, which would just be the 52.97. And then e to the 0.1156 70. And then you could put that in the calculator. I'm sorry, so we get 173,117.5. Okay. And then the last part is when will the population reach 11,000? Okay, so if the population is 11,000, then this means that we need to find the time, how long that would take. So we would have 11,000 equal to the initial 52.97 e to the 0.1156 x. So we would just divide by 52.97, and I usually keep exact values till the very end till I use the calculator, which can be a little more work, but I think it's better to be accurate than be rounded off. Okay, then at this point we would just solve as we know it, and of course we're going to use natural log. So we'll have natural log of this fraction 11,000 over 52.97, and then divide by the k as usual, 11.1156, and that would be equal to your x. So we can get an approximate value there. So we can get natural log of the quotient 11,000 divided by 52 0.97, and then divided by the K.1156. And we get 46.16.